This is homework assignment number 2 in CS373, and it's all about Kalman filters. So question number 1 is measurement update. Let's start with two Gaussians and say they have identical variances. Let's multiply them. We know that the resulting Gaussian mean will be just at the center between those two Gaussians. I wonder if the new variance sigma square is now smaller, larger, or the same as either of the individual Gaussian. Please check one of the three. And the correct answer is smaller. We are more certain afterwards you get a more peaky Gaussian whose standard deviation is smaller. This is the correct answer. Say we have a prior of a Gaussian with mean mu and covariance sigma square, and our measurement has exactly the same mean and the same covariance. Suppose we multiply both and get a new mean, which is the same as the old mean, and we get a new covariance sigma square, which, as you all know, corresponds to a peakier Gaussian. I want you to express nu square as a multiple of sigma square. Just put the answer here as a real number. And the answer is a half, or 0.5. To see, let us multiply these two Gaussians over here, which in the exponent becomes an addition. We can now rewrite this as follows, where we bring the factor 2 for these two terms into the numerator as 1 over 2 sigma square. And from that we see that the new variance is 0.5 as large as the old one when applied to the squares. So as a result, you would have this equation over here. I have another Gaussian question for you. This is called a heavy tail Gaussian. So as you go to plus minus infinity, the Gaussian levels off at some finite value alpha, as opposed to 0. My question is it possible to represent this function as a Gaussian? This is the formula for the Gaussian again. Put differently, can you find a mu and a sigma square for which this exact function over here is attained? Please just check one of these two boxes. The correct answer here is no. Suppose we let x go to infinity, then x minus mu square for any fixed mu will go to infinity. So we have x to the minus infinity, which will go to 0. This is the constant. Therefore, we know that in the limit of x goes to infinity, this expression must be 0. However, in this graph, it stays at alpha and doesn't go to 0. So therefore, there can't be a valid mu or sigma square. If you're deep into probability, you know that the area under Gaussian has to integrate to 1, and this area diverges. It's actually infinite in size, so it's not even a valid probability distribution. My next question pertains to the tracking problem that we talked about in class. In class, we addressed a one-dimensional tracking problem, where we were estimating the location of the system and its velocity x dot. I'd like now to generalize this to a two-dimensional problem, where we're given a coordinate x and y, and the object we're tracking moves in two-dimensional space. And we wish to use a Kalman filter to understand where the object is, what its velocity is, and to even able to predict a future location based on the estimate of the position and its velocity. So the only difference to class is that our object now moves in a two-dimensional space, whereas in class it moved in a one-dimensional space. So my first question is, what's the dimension of the state vector in the Kalman filter? In the class, it was this kind of state vector. Now we have a new one. How many dimensions or how many variables are there? And the answer is 4. So rather than x and x dot, we have x and x dot and y dot as our state vector. And there's 4 variables. Now comes the tricky question. In the Kalman filter program that we studied, the 2D Kalman filter, we had a matrix F. And for delta t equals 0.1, our F matrix, the state transition matrix, had a main diagonal of 1, which means in expectation our location stays the same and our velocity stays the same. But we also knew that the velocity affected our state in the following way. And we could now place 0.1 instead of the delta t to get this specific F matrix. Now I want to know from you, for this new 2D case with a 4-dimensional state vector, what is the new F? This is a 4x4 matrix, so I want you to fill in all of those values. Again, please assume that delta t equals 0.1. And don't write delta t, write 0.1. And the answer is the main diagonal remains 1. This expresses the effect that in absence of any velocity, we expect the x-coordinate and the y-coordinate to change. We also don't expect the velocities to change. But the x velocity will impact the x position through a 0.1 over here. The third coordinate is the velocity and it affects the first coordinate. The same over here. All the other values should be 0. So this is the 4-dimensional generalization of this 2-dimensional state transition matrix over here. Let's now come to our programming exercise. And I want you to program exactly what we just talked about. We're given a 2-dimensional world where we observe in 2D measurements of a moving object with an unknown but fixed velocity. And using a state vector of this type, I'd like you to implement the Kalman filter. Now this Kalman filter now has 4 state variables, whereas the one we used before has 2 state variables. I will give you the entire code for the Kalman filter, but I want you to set up the state vector x, the motion u, p, f, h, r, and I, which are all those variables that define the Kalman filter. Start with the assignment that we had in 2D and make it work in 4D. So here's exactly the same matrix class that I wrote you before. Here's the Kalman filter procedure. We'll go through our measurements and apply the Kalman filter equations. I should point out there's a slight difference to the code I gave you previously, where I inserted z.transpose. It makes it a little bit easier to work with multidimensional measurements than the way I had it before. But you don't have to pay attention to this. It's just fixed. It was a kind of a bug before. And as I scroll down, the output of the Kalman filter routine will be an x and a p. In our example, the measurements will be a sequence of measurements in 2-dimensional spaces now, in x and y. Look at the x's 5, 6, 7, 8, 9, 10. The y's go 10, 8, 6, 4, 2. You can imagine what the regularity is and what the velocity is. We assume a dt of 0.1. That means when it goes from 5 to 6, the velocity is actually 10, not 1. But we won't tell the system, but we will tell the system our initial xy location, which is 4. That goes nice into 5, 6, 7. And it's 12. That blends nice into 10, 8, and 6. Our initial state vector I've already given you, which is the initial x and y, and 0, 0 for the 2 unknown velocities. And the motion vector, just for completeness, will just be 0, 0, 0, 0. We have no external motion. That's a bit confusing because there's actually motion in the system itself. But this would be more like an external change of the motion, as if someone hit the object with an external force. So it's 0, 0, 0, 0. Please don't change it. P is the initial uncertainty. And I want you to initialize it so that the uncertainty for the xy coordinates is 0. But the covariance term for the velocities is 1000, indicating that we really don't know the initial velocity. We just know the initial position. I want you to plug in the F matrix. I want you to design an H matrix that's a projection matrix from 4-dimensional state space to 2 dimensions, reflecting the fact that we can only observe the first 2 state variables, x and y, but not the velocities. I want you to define a measurement uncertainty matrix, which now is a 2x2, that has 0.1 as the main diagonal, as measurement noise. And this is an identity matrix over here. Once you design all those, you should get the following output. So when I run this, I get as an output, for my 4-dimensional example, the x-coordinates 10 and 0. And this makes sense, given that these sequences over here Here is a final measurement 10 and 0. 5, 6, 7, 8, 9, 10. 10, 8, 6, 4, 2, 0. The interesting thing that I want your program to produce is the velocities. They are approximately 10, which makes sense given a delta t of 0.1 gives us per time step a 10 divided by 10 equals 1 increment over here. And the second velocity is minus 20 multiplied by 0.1 gives us a minus 2. And you can see it over here, 10, 8, 6, 4, and 2. I also want you to output the covariance matrix, which is certain of elements that are still 0, like these guys over here. But we find that along the main diagonal, our uncertainty has shrunk substantially. It's 0.03 for the coordinate estimates and 0.1 for the velocity estimates. Remember, this number over here was 1,000 before. Here's a second example where we have an initial coordinate of minus 4 and 8. We can see the measurements 1, 6, 11, 16. It seems the increments are in x direction 5. In y direction they're minus 4. 8, 4, 0, minus 4, minus 8. If I now run this, I get for my x vector approximately 16, the number over here, approximately 8, the number over here. And these are velocities, 50 and minus 40 in approximation, which multiplied with 0.1 is our plus 5 and our minus 4. Here's yet another example. Initial state 1 and 19. You can see the first coordinate doesn't change at all, so we should get a velocity of 0. The second coordinate goes from 19, 17, 15, 13, 11. Running us gives us 1, unchanged, and 11. Velocities are 0 and minus 20 for the decrements of minus 2. And going into the covariance, we see values along the main diagonals 0.05, 0.05, 0.33, and 0.33 for the velocities. There are certain off-diagonal elements. Make sure those all match what your code produces. I can now change some of these measurements to make a noisy measurement. One way to do this is to set an oscillating measurement between 2 and 0. Remember that this Kalman filter assumes the fixed velocity. There's no way to explain these measurements by the fixed velocity. So it has to be measurement noise. So we can run the Kalman filter again. Your filter to output the following values. 0.7 for the current state, 11 as before, and here are two velocity estimates. It actually believes there's a slight velocity of minus 0.66 in the x direction where we had noisy sensor input. The covariance matrix should look exactly as before because it's not affected by the measurements themselves. So your job is to fill in these various matrices. Good luck. So here's my solution for the programming assignment, and there's many different ways to structure this, but that's what I've done. I have a dt equals 0.1. I set my initial state vector to be the initial x and y coordinates, and for the two velocities I set them both to 0. My u vector, as I said in the statement of the problem, is 0 everywhere, so just ignore it. Interesting is my p matrix that measures the uncertainty. And I set the uncertainty initially for the locations to be 0. These are the two main diagonal elements over here. And the uncertainty for the velocities to be really high, as 1,000. So this is my initial uncertainty matrix. That guarantees that I can really estimate the velocity based on data. And I believe that the initial state estimates are correct. Our F matrix is the four-dimensional generalization of the F matrix we had before, where we have 1 along the main diagonal. This one says that the position is retained in expectation and velocity is retained. And we have two dt's over here. The x dot, which is my third state vector, influences the x by a factor of dt for each time step. And the same is true for y dot. So these are the places where our velocities impact our position estimate. And then as I scroll down, the H matrix is a 4x2 projection matrix, where we project out the x dimension and the y dimension without any velocities. For the measurement uncertainty, I assume that each measurement has uncertainty covariance of 0.1. And these are along the main diagonal of this 2x2 measurement noise or uncertainty matrix. And this is obviously how a four-dimensional identity matrix looks over here. So if I run this for my first example, where the measurements are 5, 6, 7, 8, 9, and 10, In the second dimension, 10, 8, 6, 4, 2, and you can't see it, but it's 0 over here. In my output, I correctly get the estimate of 10 for my x and 0 for my y. And the velocity is 10 and minus 20. And as we had before, because dt equals 0.1, a step from 5 to 6 within a tenth of a time unit requires a velocity of 10. And from 10 to 8, one of minus 20. These numbers are correct. We can also look at the covariance matrix. And it's hard to read anything off it other than we are fairly certain as to what our location is. And we have a very good estimate of what velocities are. Our covariance of velocity uncertainty is 0.1. And this is down from 1,000, which was the initial value in these uncertainties. Going to the second example, I now commented away the first example and put in place the second example. If I run it again, here we see the first dimension go from minus 4, 1, 6, 11, 16. Second dimension 8, 4, 0, minus 4, minus 8. And these are the exact same values over here, 16 and minus 8. For velocities, I get 50 and minus 40, which are exactly the correct velocities. Finally, for our third example, where the first coordinate doesn't change at all, you get the correct 1 over here and velocity of 0. Second coordinate goes from 19 to 17 all the way to 11. You get 11 over here and velocity of minus 20. So this is the implementation I wanted you to do. If you implemented this thing over here, you got it right. And congratulations, you implemented a fairly non-trivial Kalman filter in stages, but through this class you now have code that allows you to run Kalman filters on complicated problems. And I hope you really got an understanding how the Kalman filter works. So congratulations, you just made it through the Kalman filter class and the second homework assignment. You've implemented Kalman filters, you learned a lot about Gaussians, and you wrote your first vehicle tracking software. Congratulations, that's actually really, really cool. Next week, we'll talk about particle filters. It's yet another method for state estimation. It is very interesting and very fascinating. We're going to implement our first. See you next week in class.